Hey guys, I'm recording this video upon heavy request by many of you. Apparently you're frustrated that UNet or any other network for semantic segmentation, if you want to train it from scratch, it takes tremendous amount of training data that you probably don't have. Most of you may not have like the enough training images to begin with. And on top of that, if you have them, may not have 6 to 9 months of time it takes to actually label every pixel of every one of your 2,000, 10,000 images. So let's look at how we can use transfer learning, especially VGG features. We covered this in the last couple of tutorials anyhow, but now let's apply that for semantic segmentation to see how amazing the results can be, even with limited amount of training data. So just to remind you again, when we say VGG16, it's a convolutional network model, right? It has 5 blocks and each block has 2 convolutional, well, the first 2 blocks has 2 convolutional layers and so on. But as you go through these convolutional layers, the size of this image actually changes. So if you want to use it for features, for example, if you take pre-trained weights and use it as features, then it's fine. You can do that if you're doing fully, convolutional and the neural network. But if you want to chop this off and then combine it with random forest, it does make sense to chop it off to a point where the image dimensions do not change. And I'll explain what that means when we get to the code part. Okay, so don't worry about it. So we're going to take only the first 2 layers. Again, we are taking pre-trained weights. We are not just taking the network and then training it completely. We're not even training anything. We are just taking pre-trained weights. And why VGG16? Well, you can take any architecture. It doesn't matter. I like VGG16 for image processing because it achieves very high accuracy on the imagenet dataset, which is not an easy thing to do. And it has been trained for weeks and weeks, I think for a few months, using NVIDIA Titan GPUs, and there is no way I have that type of resources or the type of time to devote to myself, my data for training. Why do that if someone else already did that? That's why transfer learning is very important. And ImageNet, in case you don't know, it's 15 million labeled high resolution data sets. If you have the time and resources to kind of load all of this, create labels, fine, go ahead and do that. But let me show you a trick in terms of how to use it. And I think I don't need to explain what transfer learning is to you. Please watch my previous video in case you wonder what that is. Now, you just saw this image. The reason I showed that image is, first of all, what do we mean by labels? Where do we get these labels? Of course, you have to have some labels, right? So you can tell exactly what the ground truth is on your own samples. How do you do that? Let's look at this example. In this case, I have a folder called train images, obviously, where I dumped a whole bunch of training images, and these images are pretty large. If I open this, in fact, you can see each image is, I think, 1K by 1K or 996 by 1024. It's almost 1K by 1K. That's not, that's 1 megapixel per image, so that's pretty large image. For deep learning, you typically break your images down to, 128 by 128 or 256 by 256 and then train it. But now I'm not processing anything. You don't have to cut down your images unless you deal with extremely large images, but 1K, 2K by 2K, even 4K by 4K if you have enough RAM is fine. Convolutional networks can handle these large images. Once you go to dense networks, it can become a bit of an issue, but all we're doing is feed forward convolutional and just applying pre-trained weights. So large images are okay. Okay, so for each of this image, I actually have corresponding masks or labels, and the mask actually looks somewhat like this. You already saw this on the screen. So if I drag this, make it a bit larger, you can see, okay, in this image, I have 1,000 of these images. I want to segment them. So I picked like 10 of these and occasionally, painted some of these pixels saying, okay, the bright ones, they have a pixel value of 4 in this case. And the dark region is pores and background. So it has a different pixel value. In this example, I gave it a pixel value of 1. And a pixel value of 0 is everything that I haven't labeled. Okay, so how did I get this? Well, if you don't have a way of labeling your own images, then just go to APEER.com, okay, which is www.apeer.com. Go ahead and sign up. This is all free. Everyone gets about 100 GB of free storage. Great. And it is an online image analysis platform, so you can find existing modules, which I'll talk about in a second. But once you log in, you can go ahead and upload your images under Files and click on this I button. It opens up a new window and you can just paint your pixels. Okay, it's very intuitive. Otherwise, just watch the videos that you find on APEER. I don't want to make this an APEER training class, but if you want, tell me. I'll talk about APEER all day because this is what we do at work. Okay, so one other thing I'd like to show, what the code that I'm about to go through, I already created an APEER module out of it. It's very easy, which is a Docker container, and published it online. So you would see these modules, random forest predict and random forest train, and we already published a workflow, like put everything together into your workflow. So all you need to do is upload an image and then get the result. And just look for this called image segmentation using random forest. In fact, my colleagues from India, they helped finish this module, so thankful to them. So go ahead and run this. In fact, go ahead and edit it. You can see how the structure looks like. Okay, and make sure you're running the latest version for each of the modules. Yeah, version 2. Things always change. And input your image, input the labels, and input any other images you want to segment here, and just go ahead and run the workflow. Everything runs in the cloud. Okay, that's it. Let me promise to get back to what our intention is here. Okay, now our goal is to take VGG pre-trained weights, use it as feature extractors, and then segment our images using random forest. I will go through these steps a bit quickly because I did cover this in the last 3 videos. Watch 158, 158B, 159. So we did cover quite a bit of this. Okay, so I don't want to waste your time talking about these. Okay, and for those of you, this works. I mean, I tested this on TensorFlow 1 point something and Python 3.4. And in this case, I'm using TensorFlow 2.2 and Keras 2.3 and Python 3.7. But there is nothing tricky with this code that makes it not usable on other versions. Maybe the VGG, but I can't think of any reason why it doesn't. If not, go ahead and leave a message. Okay, these libraries are pretty standard. We have imported them quite a few times in the past, so I'm going to import those. These are also very standard. From Keras, I'm importing sequential and model and convolutional 2D. Why? Because, maybe I'm not even using these, but I just import them all the time. The important thing here is from keras.applications VGG16, import VGG16. Okay, this is where we are going to import the weights. We did exactly the same in our video 158B, where we used this pre-trained network for image classification. Now we are doing pixel classification, which is semantic segmentation. Okay, that's the difference. Okay, so let's run this line. So it imports VGG16. And now I am going to just look at, okay, what directory we are. So we have 3 subdirectories within there. We have to go ahead and look at training images. We'll get to that in a second, but first let me define the size. You don't have to resize it. The reason I'm defining size X and Y here is so I can resize my input images. If they're all different sizes, then it doesn't work, right? So if your images are all of same size, that's fine. You don't have to resize. But I just do this anyhow, just to make it's a sanity check, okay? So now I'm creating an empty list to capture all the information about the training images, which I'm going to populate as I go through this for loop. What am I doing in this for loop? Just going through each image within this subfolder, looking at images with an extension of TIFF, reading them using OpenCV, which means you can use any other libraries. I'm reading them using OpenCV, I'm resizing them to whatever the size here, and then converting them from RGB to BGR, because remember, OpenCV just reads images as BGR. I want to convert to RGB, and I'm just appending them. Finally, at the end of this, let's run these. Did I do that? Yeah. So these train images would be populated, and we have 8 images, right? So these are the 8 training images we have in the folder. Now, lists do not work very well with any type of math. So let's convert that into a NumPy array. So that's all we are trying to do here. Let's do exactly the same with train masks. Again, remember the train masks is all of these images that I trained or labeled on APEER and then downloaded them. In this case, they're all single files, but you can just create a TIFF stack out of it to make your life easy. So you don't have to do one single file. Obviously, in that case, you change how you're reading the images, but otherwise everything else should be the same. Okay, so let's run these lines that are exactly same as reading our images. And now these lines are basically, typically when you deal with these variables, we label them xtrain and ytrain, right? So that's pretty much it. I'm just reassigning it and I'm expanding dimensions. In this example, this expanding of dimensions is not necessary, but I copied the code from my last time, so I just left it. No reason, again, go through this line by line. I'll share this code, don't worry about it, and go through this line by line. Okay, so VGG model. So now here we have a VGG model that we are importing. Again, remember this VGG up here that we imported. So basically now we are using that and assigning it to a variable called VGG model. And we are also going to import weights corresponding to the weights from imagenet and include top equals to false, which basically means do not import the dense layers and the output layer. That's pretty much it. So let's run this line. And in fact, if I do VGG model.summary, you should see that being printed here. And here is the VGG model. My input, the traditional VGG model input is 224 by 224 by 3, I believe. And here we are just changing my input to input shape size X, size Y, and 3. So it's not like you are forced to use 224 by 224 by 3, okay? So we changed the size there, and you can see if you come down here, it says trainable parameters 14.7 million. Of course, we're not going to train all of this. So in fact, we don't even need this because we're not training anything at all. But let's go through these two lines. What it does is it actually makes all of these non-trainable. So if I print the summary again, now you see the trainable parameters is 0. So all I did is each layer, we just set it as non-trainable. That's it. Okay. Okay. Now I don't want this entire thing. If you see, we start off with 1024 by 996. That's the input. Conv1, 1024 by 996, 64 features. Convolutional 2, 1024 by 996, 64 features. And then max pooling, and then conv2d, 512 by 498. That means my image dimensions are changed here. Okay, I can modify this, but it's fine. These weights are more than enough for us for now. Okay, so in summary, what I'm trying to do is take only block 1 conv1 and block 1 conv2 and then extract features out of this, because my y, okay, if you look at my y train, look at the shape of y train, 1024, 8 images, 1024 by 996, okay, by 1. If I change the shape to 512, if I change my x shape, I have to think about, okay, and now I need to change my y shape into the same thing and all that stuff. Okay, let's stay away from that for now. Okay, so I hope that makes sense, which means now let's go ahead and define our new model. My new model that I'm defining to extract features is the model where my inputs are same as inputs for VGG model. Okay, and my outputs is VGG model.get layer. This is important. So this is where you need to understand how to chop off the input, you know, the model that we actually got. So this is what I'm basically saying. Okay, VGG model get layer block 1 conv2. So I'm just getting this layer block 1 convolutional 2 and the weights corresponding to that. And this is what we'll see in as a summary in a second. Okay, so we executed this line. Now let's look at the new model summary. Okay, the new model summary is my inputs are, remember, same as the VGG input, which is this that we just defined. And we have conv1 and conv2 because we want to stop at block 1 convolutional 2. I hope this makes sense. And we are not training anything. The trainable parameters are 0. Okay, so now we have the model that we want with the weights. So this is my feature extractor, which is the next step. My features is basically my new model dot predict. I'm just predicting on what? On my X train. And remember the X train shape is 8 images by 1024 by 996 by 3. Okay, so let's go ahead and apply. So this generates features in a second. Okay, so now let's look at the shape of features. The shape of the features, the features that we just generated is 8 by 1024 by 996 by 64. Remember, this should be the same. That means I have 64 features that are going into random forest. This is it. Okay. Now, if you want to visualize how these features look like, you can basically just write a few lines of code to just map out all the features that are coming out. And let's have a look at it. There you go. My plots are in a different window. Let's resize this a bit so you can see this a bit clearly. So here are the features. I mean, it's tough to see at some locations, as you can, I mean, I can squint to see this, but you get the idea. You can plot it out, each feature, you know, in a large way, and then have a look at it yourself. But these are the features that we just generated. So that's it. Now we're all set to supply our X and Y to random forest and train the random forest. So I'm reassigning my features to X because that's what we use typically, right? It's easy for us to think in terms of X. And if you look at the X shape right now, it's 8 by 1024 by 996. Let's collapse all of these 8, 1024, 996 into single column and then have 64 in a different column because that's what random forest takes in, right? So let's go ahead and reshape this. So now my X is how many ever, 8,159,232 of these pixels and 64 of these columns. Now remember, most of these pixels are just background pixels with a pixel value of 0. Because when we label this, most of these unlabeled pixels have a value of 0. Only the labeled ones with values 1, 2, 3, 4, and so on are the ones we want to use for training. So I'm going to drop all the pixels with a value of 0 in a second. But let's also shape Y to bring it to the same shape here. So our Y is 8,159,000 blah, 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 same as X. Okay, now we need to drop same pixels from Y and X where my Y equals to 0. The easiest way to do that is by creating a data frame using pandas and combining these. And let's go ahead and run these lines of code. Now you can see my pixel value is 0. I have bulk of it, 7.8 million data points have pixel value 0. Why waste our time training on all of these if they are useless? Okay. And pixel values of 1, 2, 3, and 4, these many. It's not very well balanced, but that's fine. Okay, so the next step is to drop all the pixels with a value of 0. So there you go. And if I actually print these two again, you should see that now my 0 is gone. I only have 1, 2, 3, 4. Okay. So far, I hope you're fine. Now, let's redefine our X and Y, right? I mean, now we have a data frame. Now, what is my X? X is every column except for the column labeled label. And my Y is only the column labeled label. So that's what I'm trying to get here. And my X and Y are defined for my random forest. Now, I just need to import the random forest, though I like the one from scikit-learn. Unfortunately, I cannot find a random forest that uses GPU for acceleration. If you guys know, please let me know, but this one uses CPU, so it's a bit slow, but still much faster than deep learning. Okay, let's fit it. This may take a few seconds, so I'll pause the video and continue as soon as it's done. Okay, so after about a minute or so, this is done finally. So let's go ahead and save the model because now if you think this is working fine, you may want to use it to segment a lot more images. So let's go ahead and save this model. And for that, I'm using Pickle. Okay, and let's go ahead and load the model again. Well, for now, I don't think we needed to do that, but just so you know, you can do this. Okay, let's test this on an external image. In fact, in the folder test images, I think I have one image right here. So let's open this and let's actually see how this works on this specific image. So let us minimize everything and let's load this image. And again, all I'm trying to do is basically use OpenCV to read it, resize it if it's needed to be resized, and exactly the same operations we did before, right? So including expanding the dimensions. So everything looks good before going into our model.predict. Again, we are extracting features when we do new model.predict, right? We have to do exactly the same steps. We have to extract the features and then predict. Okay, so we are extracting the features, and XTest feature, if you look at that, the shape of this is 1024 by 996 by 64. Okay, so let's go ahead and reshape this. And why are we reshaping? It's because we are collapsing everything into these two columns. That's exactly what we did for random forest. Now we are ready to predict it using our loaded model. That's it. So let's go ahead and predict it. This should be relatively quick, even though it's a large image. And once it's done, we are going to reshape it to the original shape of our 2D image, and then view it, save it, whatever we want to do. So let's do both, viewing and saving. And let's save it. Prediction image is not okay. I'm not sure if we did the reshape part, maybe not. Now let's run these two lines so it actually saves it. If you look at the plot, there you go. That's the predicted. I'm saving it for a reason, because it's easy for us to see. So there you go, the new image, segmented. And let's put this other image. If I opened it, I think I already opened it somewhere, but there you go. In fact, a better way would be doing this. That's not bad, actually. That is pretty good. Again, all of this region that you see that looks like, you know, a bit dull and porous, that's a different phase. The bright is a different phase, and this is not bad. Maybe I can use a few more labels, but in general, this is a pretty good segmentation, I should say, even with the limited number of labels. Maybe a bit more labeling can improve certain areas, especially when I see some of these boundaries. No, even that one is not wrong. So there you go. Now you know how to take advantage of pre-trained VGG weights. If you don't want to code all of this, again, you can always go to APEER.com and go ahead and use whatever the tools that are present on APEER. Okay, thank you very much. And again, in the next tutorial, I'll try to find another trick that hopefully you find useful. Thank you very much.